Hello again. So in this follow-up video, we're going to talk again about bskSim-based simulations. And I'm going to assume you've already gone through the first video that's inside basic orbit simulation within the bskSim section. This is where we talked about how to set up a simulation using classes that each contain all the processes, tasks, modules, and how to connect and do all this and all the benefits of that. So here, let's just jump right into attitude. This is essentially a scenario attitude feedback with reaction wheels, where you can use a spacecraft, some sensors like simple nav, connect an attitude, have a guidance, like I suppose to point here in inertial 3D space, come up the tracking error, use an MRP-based feedback control, and then send it to reaction wheel commands. If we look at what that would look like in a bskSim-based simulation, we can see on the right-hand side, that's what we discussed before. We had a single dynamics task, which had a spacecraft, it had wheels, it created external force torque effectors that we didn't really use last time. There's gravity body, so for Earth, Sun, and the Moon. The Moon's not shown here, but that was included as well, if you remember, and the SPICE interface that specifies them all, and there's a variety of other modules that are created. So we're using the same dynamics class that we played with last time. But now we also want to turn on the flight software side of it. If you remember in this earlier simulation, the mode request was standby, which as you will see, just turns off everything flight software related. Now, with the flight software side of it, we're not just going to have a single process and a single task, but we will have a single process, and embedded in a process will be a whole series of tasks. So there'll be chunks of the flight software execution assigned to tasks. They could run at different rates if needed. But the reason we're chunking them up into tasks here is because in Basilisk, you can turn off tasks and turn on tasks. So you can configure stuff, but then never evaluate it unless you need it. So in sun pointing, you may need these modules. In hill frame pointing, you need different modules. But in both cases, we have to take an attitude guidance message and do an MRP control and send a control command, right? So there might be some commonality. So by having these things in tasks, it allows you to group and chunk them together, evaluate them at their required states. But we have to show how to turn them on and off, and that'll all be in this code. If we use the documentation figure here, this is somewhat handy. We can just play with, in this scenario, two different flight modes. One's called inertial 3D and one's called direct inertial 3D. And you'll see what the names mean in a moment. So inertial 3D, this is the classic scenario, the attitude feedback with reaction wheels. We used inertial 3D as our reference generation. We pointed somewhere in space. This is how you're supposed to point, like the Hubble pointing at a star. Then we computed the tracking error. So from here, from the dynamics, there was a simple nav module from which we would actually connect. That connection is actually not shown here. That would feed in, right, tracking error. And then the tracking error got fed to the MRP feedback, which then would map, that gives you a control torque. Then you have to map the control torque onto the motor torques of reaction wheels. And those motor torques should drive the actual physics of the reaction wheels, and the sensors is a reaction wheel sensor that gets fed in, and that's where we go there. So anyway, that's the basic scenario. Now here, there's this box indicates one task, this box indicates another task. So the inertial 3D task is the guidance and the attitude tracking error. That's in one task. This other task has the MRP feedback and a reaction wheel motor module, and that should be connected here to the reaction wheels. In contrast, direct inertial 3D is the same guidance, same attitude tracking error. Then there will be an MRP evaluation, but the output of that needs to be fed directly to an external force torque. So this is like the scenario attitude feedback, where we just computed an external control torque and applied it directly. So by changing flight modes, I can actually switch between both configurations very quickly. That's pretty cool. But there's some challenges. This module for MRP feedback will be connected and evaluated differently from this one. If this one were always evaluated, then we would always get a motor torque, and that might be then applied and sent off to the wheels, which we don't want. So here, we're going to choose to make two copies of MRP feedback and add them to tasks where it makes sense and connect them how it makes sense. That's one way to deal with this. There's other ways you could have done it too. So that's there. If you look at some of the other examples that are in here, this one, for example, is attitude guidance. It's one where we're using hill pointing. So there will be a different mode, a task for hill pointing, where we have hill pointing and attitude tracking error. And if you look at these, the inertial 3D or the direct, these, well, the inertial 3D task is the same. It has inertial 3D and tracking error. In this case, it's going to be the same tracking error module. And that is handy because we just have to have one instance of it. You could make a special tracking error module per flight mode if you wanted to, but that would increase on a flight computer your memory footprint because now we have lots of instances that we have to run. So here we're going to show you how we can use one module actually also across different tasks, but we have to make sure here, you know, tracking error should be subscribed to inertial 3D. Here, tracking error should be subscribed to hill pointing. Well, you can't be subscribed to both at the same time, or can you? There's a thing that we call gateway messages. They're basically externally created messages. You've seen this already in flight software when we have to create vehicle configuration data message. It's the message in flight software that contains the information about the spacecraft inertia. So things like MRP feedback need that, and reaction motor torque needs a different message about the standalone message about the reaction wheel configuration data. So we can make standalone messages, and we will talk about how this is going to work here in a second. So hill point, this will be one task. This task is the same MRP feedback. It's really the same task as here. So we don't have to duplicate that code. We just have to enable that task and disable 3D task and enable hill pointing task. And then we can switch between them. And this becomes very elegant in how you can start to switch around and configure lots of different configurations. Let's look at the rest of them. Here's one velocity point. So it's just like hill pointing, but velocity pointing. Velocity pointing cares about the planet states, the spacecraft states. So there's a variety of connections that have to be made, but that's in its own task. And again, we're going to have the same repeated tracking error Basilisk module. It's just going to not connect subscribe to velocity point directly, but to a standalone message that will have the attitude reference. And just last, this is a different scenario, attitude steering. Here we're using hill pointing, so that's the same. But now we're doing not MRP feedback, but we're doing MRP steering, which has two modules, MRP steering, and rate servo, and then reactional motor torques. So those get created. I think it's the same reactional motor torque that gets run in both cases on those tasks, the same module. So you can see, you can start to mix and match in all kinds of interesting ways. But there's always this challenge of, wait, I have multiple modules that are going to write an attitude reference message, and attitude tracking error in all cases needs to subscribe to that message. So let me share my iPad screen. And there we go. That should be up and running. So here I can draw a little bit and show how this would work. So let's pretend, you know, we have some module running. This could be a series of modules that are running in a task, and they execute. And then afterwards, we have other modules that have to run, and they would execute, and we would connect these, and this one would connect all the way down directly to this task. And that's good. And we were talking about chunking, so let's do a little chunking. Let's say this is one, let's say, you know, the inertial 3D with wheels, kind of just the inertial 3D guidance task. You might have other modules, let's go back to black, you know, that are in a different task that do other things. This could be the hill pointing, the velocity pointing, something else, right? Now, these modules here have to either connect, you know, the modules down here have to connect to either this module or this module, but you can't connect to both. That doesn't work. The subscribe to connects to the memory location of that particular module. So what we're going to do then is we are going to actually enable the red task disable the green tasks. So only one of them at a time is going to write to an attitude reference message. But it can't write to its own output message. Every module contains one of those. So let me go back to black. So the problem is we can't connect to the output message that is inside the module. And the workaround will be, we will just make an external, for example, attitude reference message. And now, instead of connecting directly this lower module to the upper module, left or right, what we do instead is this module is going to connect to this standalone message. So in all cases, there's only one attitude reference message. An MRP, the attitude tracking error, for example, would only read that message. But now the red box and the green box need to evaluate a solution. And instead of writing to their own message, we need to redirect this one to actually write to this external one. And this one is redirected to write to this external message. It's the same one. So up front, this looks like a conflict. Wait a minute, I have two modules writing to a message. Won't you just get the message that whoever was last wins, right? That's the message that you would read. And of course, if you just ran all the modules all the time, you would get a complete mess that we just described. So the trick will be, we have to ensure that in the right flight mode, only the right tasks are being evaluated. So if you're in sun pointing mode, maybe only the red box gets evaluated, and then attitude reference is computed from there. If you're in hill pointing mode, then only the green box will be evaluated, and the modules in the left box don't get executed. They'll be disabled. They're not deleted. They're in memory. They're just not being executed. And that's achieved by enabling and disabling tasks. This is why it's handy sometimes in flight software to not just have one mega big task and all the modules are in it, but we might break it up. And then we can disable chunks of them at a time and leave connections and subscriptions all intact. So this attitude reference message here is what I call a gateway message. It's essentially just a standalone message. But we will have to see, and that's in the earlier documentation as well, when you talk about messaging, but how to redirect. A module by default will write to its own copy of the output message, but we want to redirect it to say, yeah, no, don't write to your own copy, write to this other one. And here, in this case, it's going to be a standalone message object. Okay. Now, let me share my screen again. Okay, we should be back. So that's the premise. Let's now dive into the code. How does this all come together? We're going to look again, we're going to start with the first script, which is scenario feedback reaction wheel. And if I just jump to the bottom, this should look really familiar. We're going to create an instance of this class, scenario attitude feedback. So all the simulation is put into the class. And this class, like before, when we had that basic orbit one, it's a subclass of bskSim and BSK scenario. So we've already discussed that in the prior video. So at this point, when we have that instance, we're now going to run the scenario. We put all that into a separate method, and it will run initialize. Let's see if you paid attention. When we create an instance, you will find all in the initialization, it sets everything up. It configures, it initializes, it sets up the recorders, it does all of that stuff. When we call run, we're going to now initialize the simulation explicitly, right? Here, it's the Basilisk modules that are being initialized properly. Now we're initializing the simulation, and that means we're setting up where is the spacecraft. It's on a polar orbit, it's on an equatorial orbit. How is it oriented? All of those things. Same as before. We're setting the simulation time. The mode request instead of standby will be inertial 3D. We'll see standby in a second, and you'll see why standby just basically turned everything off. We configure the stop time, and we execute it. And then here, I want to run for an additional 20 minutes. So I set my stop time to 10 plus 20, which is 30 minutes. And I'm going to switch from inertial 3D to inertial direct 3D. So I'm switching my flight modes. 10 minutes where I'm using the wheels, and then 20 minutes where I'm using an external fork control torque instead of the wheels. This could be coming from thruster sets, for example, to control the attitude, and it should converge, point, and do what we need. And then the last step, same as before, we pull the outputs from the recorders and plot it. So the simulation, you can see there's a lot of same code, nothing much new here, except that we're going to start and stop and set the flight mode differently. And we have to set up events that will monitor the flight mode and go, ooh, something else is asked for. And then we'll have to turn on and off these tasks. So we have the right combination of modules being executed per that flight mode. Okay, so let's go up again. This class, we initialize everything that we should, give it a name. There's some class variables that I'm initializing here. As before, I'm setting the dynamics to BSK dynamics and the flight software, BSK flight software. That's the same thing. So we're using the setting functions. These are the ones here in the master class where we specify that and it creates the process. So after this, I have a process in the parent method, in the parent class for the dynamics and a process for flight software. Next, as we did before, we have to run the configure initial conditions and we have to do the log outputs. So when we create the process, we're also creating an instance of the Basilisk dynamics, BSK dynamics model, which was in, that was basically, if you look at the BSK dynamics, that was the class name. And in flight software, we call it BSK flight software models. Sorry, where was I? Here. So that all happened in these commands. So all of that now is the same, and that's already configured. Here we're configuring our simulation and then the outputs. And if you want to do modeling, enable visualization, I've got some code here as an example. Same as before, we can enable that as well. By default, it runs, but doesn't actually save to a file, just so we don't create massive files on people's computers. So configuring, we set up the orbits. You can see here, we're going to have to get a dynamics model. From the dynamics module, we get mu. From mu, we're setting up these elements, the position, the velocity, and then also set up attitude and rates. Logging, we want to get something logged. Let's see, we're doing from the dynamics, I'm trying to log my wheel speeds in this case. And from flight software, I'm trying to log the commanded reaction wheel motor torques and the attitude guidance message that shows you B relative to R. How well are we tracking? We should see that get smaller and smaller and smaller. And then we add those to the task name of the dynamics. So all the logging is happening actually in the dynamics task, the way we set it up. But there's the get function for dynamics that we used last time. Now we have some modules to record or some messages to record from dynamics and some from flight software. There's also a get function that we saw here. Get flight software model, and that returns that handle to you. So this is all pretty much the same. Pulling, you just basically now have these recorders that we had set up. You pull the data, plot it to your heart's delight, do whatever analysis. So it's very, very similar. And you can see this is very powerful that all of a sudden we can switch flight mode behaviors with just a few lines of code, and you can iterate and do all kinds of interesting analysis. But somewhere, you know, nothing is for free, right? So how does this magic in flight software work? And that is really all inside here. We're including flight software, and then we're setting that as a flight software module. So this script has a class that contains all the flight software stuff, including the processes. So whereas dynamics was a single process, flight software is going to have a whole series of processes. Sorry, I said that wrong. Dynamics had a single task within the process. Flight software is still single process, but it's going to have lots of tasks inside. They can run individually. So knowing that, let's go through this. We have some class variables. These are some standalone messages that I'm declaring to be none. These are just class variables right now. So Python asked me to initialize all the Python variables. They will be set to proper messages further down, as you will see. I'm creating my process name from the parent class, the master class. I'm setting my flight software update rate. So that's the tasking update rates here. And I believe we're setting up tasks that are running all of them at the same rate. So whatever the default was every 0.1 second, so 10 hertz. You could make them run at different rate if you wanted to, but we're trying to keep this example simple. Then, as with dynamics, we basically punched out instances of all the Basilisk modules that we have to use, but they were C++ modules. Here in flight software, all the ones we're using are C modules, C Basilisk modules. So as before, it's always a thing where we set up the configuration, the data of that module, and then we have to make this wrapper that creates the Basilisk module with that data. And that gives you unique instances of C Basilisk modules. So I'm setting them all up. You can see here the inertial 3D, the inertial pointing, the hill frame pointing. There's a sun-safe pointing configuration. There's a velocity pointing module. This is a weighted least squares flight software module that takes core sun sensor signals and computes the sun heading. There's the attitude tracking error one. And you notice it's only one module. So we're not going to have lots of copies. We're going to share one across the tasks. But we have 2 copies of MRP feedback. And again, if you looked at the reason for that, that was here, because once MRP feedback needs to be connected, the reaction motor torque reads that output message that's contained within it. And here MRP feedback needs its message connected elsewhere. And we don't want both to happen at the same time. So we've made 2 distinct modules here. Again, I'm not saying this is the only way you could have done that, but there's 2 modules of MRP feedback. I just have to give them unique names. So one's called MRP feedback control, that's direct control, and one's MRP feedback RWs, that's the control. That's where we're using reaction wheels instead of direct control to control the satellite. MRP steering, rate servo, and then the reaction wheel motor torque mapping. Those are all the final modules that are created. Okay, so pretty straightforward. We punch out all the modules first. This is all still part of the initialization. So when we created that instance, after that, all these modules exist, Basilisk modules. Now we want to set up these gateway messages. This is where we're creating these standalone messages. So if I jump to that, you can see I'm giving the SimBaseClass in case that's needed. And then I'm creating here these standalone messages. And this is the syntax. You have to include cmessage.py. This is the Python wrapper for C-wrapped standalone messages. If you use the standard messaging Python library that gets included, what happens is you get C++ message objects wrapped to be available in Python. With this syntax, you make Python created C-wrapped message objects. It's basically a C structure which contains the header, the payload, pointers to headers, and pointers to the payload. So it's a little bit different. So, but because we're dealing with flight software in C, C code only knows how to write to C structures. It doesn't know how to write into a C++ object. That's why we have to be careful. When we subscribed between modules, it didn't matter if it was a C module or C++. There was magic under the hood happening that would connect in the right way and know which methods to call to do that. But with this redirecting, we're really digging actually deep into the code and telling the C code, instead of writing to here, write to this location. And it has to be done in a C compatible way. So anyway, lots of chatting. So we're making now a standalone commanded torque message, a second commanded torque message for the direct messaging. It's the same message type, but I need 2 different instances to the way everything's going to be routed. I have here my attitude reference message that we discussed. This is what's going to be connecting to attitude tracking error module. There's the attitude guidance message that'll be connecting in different ways. And then there's the standalone reaction motor torque message that we're going to create as well. This command 0 is just set up for convenience because I can run it here, but I also have to run it elsewhere. It'll zero out all these external messages. It's nice because when I switch flight modes, I don't want to inherit something in that message, the first run, that might be from a previous flight mode, not from this flight mode. So just to be a good citizen, every time I'm going to switch flight modes, I'm going to zero all these external messages and then re-execute my code. And that's what I'm doing here. Okay, so that was setup messages. That's where we're here. Okay. The next one is initialize all of these. This is very similar to what we did with the dynamics modules. If I go look at its definition inside, you can see, again, it's a choice. It's a series of methods that configure all these different message objects. I'm going to go to the first one. Here, I need to create that vehicle configuration message. It's the flight software message that contains the inertia. So I'm making the content, specifying that content, and then writing it to this standalone message right now, VSC message. And that's it. Reaction wheel configuration message, same thing. Set the reaction wheel motor torque. This will actually, in the motor torque, configure the right axes, make the right connections. This one, for example, the vehicle control in, it doesn't subscribe to a module's output message, but it subscribes to one of these standalone messages. So there will be multiple modules that will be redirected to write to this standalone message. Versus, here, for example, we're adding ourselves, the output of this module is also going to go to a standalone message. And so we have to use this command for this message type to add ourselves. This is the reaction wheel motor torque modules. Its reaction wheel motor torque out message needs to be redirected to write to this standalone commanded reaction wheel motor torque message. And finally, this module's in message is going to subscribe to this standalone message. That's the one we just set up earlier, the flight software configuration message. Reaction wheel configuration message. There we go. Okay, so we needed that. So you can see, it's just, you have to be careful now when you're connecting, because we'll have some messages being standalone, some we're using the embedded messages in modules, and you have to make sure you subscribe to the right type of message. Otherwise, you won't get the data flow that you expect. And there'll be more. We're going to go through those a little bit more in a little bit. So we create all the modules. We create the standalone messages. We zero all of those in there. Now we need to go and configure all these modules and make all the right subscriptions. Next, we're going to create tasks. In the dynamic side, we just had one task, and all the dynamic stuff is added to that one task. Here, we're actually creating a whole series of tasks. So you can see one called inertial 3D point task, hill point task, sun safe point task, velocity point task, MRP feedback task, MRP steering with reaction wheels task, and MRP feedback with reaction wheels task. And they're all running at the same process time step, sorry, task time step, not process time step. And then they added some priorities to which one should be evaluated before others. So you can do that. But again, not all these tasks will be running at the same time. This, if you look here, this is where we're going to start to create a task with just inertial 3D and then tracking error. So the inertial 3D point task, I add now these modules to these tasks, and you can find some modules like added to tracking error. That Basilisk module can be added to multiple tasks. If you would execute multiple tasks that contain the same module, that module would be executed multiple times in a single update, which probably doesn't make sense. So again, we're requiring only certain tasks be executed at a time. Now, so this inertial 3D point task, that's the inertial 3D, it generates a reference message. And here we're going to go added to tracking error. And that's what that task should evaluate. Hill pointing uses the hill pointing module, and we'll see in a moment. We'll go back to how they were all set up and defined. And the same added to tracking error. Sun safe point has to evaluate the weighted least squares from the core sun sensor, and then it has this module, the sun safe pointing. It's a 2D pointing module that uses the sun heading and steers your solar panels to point at the sun. The velocity point has the same tracking error. MRP feedback control wrap that just runs the MRP feedback. That one we see here. But I know its outputs have to be connected directly to the external force torque, not to some other module. MRP steering, there's a steering law, there's a rate servo law, and then a reaction wheel motor torque mapping. Or MRP feedback can also be connected to reaction wheel motor torque mapping. So again, we're reusing the same module, but in between, there must be a gateway message because we have different modules writing to that. Either the rate servo writes to the control torque, or the MRP feedback writes to the control torques. And then this has to be read in. So that's also achieved through one of those gateway messages. So hopefully you get a sense a little bit of how we can mix and match and put this all together, but sometimes it needs these gateway external messages, what I call gateway messages as glue. So now we have a lot of tasks created. Not all of them should be running at the same time. So the first thing we do now is, by default, on construction, we're turning everything off. Disable all tasks. So on a process, there's this call. This is from simulationBaseClass. There is a method called disable all tasks, and so from the simulation base, which is our main simulation architecture, the flight software process, right? That was where is that? Here we go. Here's that flight software process that was created. We call disable all tasks, so now it'll disable all the flight software process tasks. And now we can use the event system. We saw this in dynamics where we can use the event systems to trigger reaction wall faults. Here, we're going to use the event system to trigger different flight modes where some tasks are turned on, some are turned off. And then we can do hill pointing versus inertial 3D pointing, or velocity pointing, or all the different modes that we want. And you can see, so as before, that each event has to have a name. I'm just calling it initiate standby because there's a standby mode. I give it this time. I'm setting it to true. That it's created and active, this event. It is available to be considered. The next line here, this is where we're giving it a condition that it will check. And again, it's just a list of, it's a string inside a list. And the condition then is, if this variable mode request, you might remember that from our simulation, this is where we specified mode request. We called it inertial 3D. But here it's checking if it is standby, which is what we made it in the basic simulation last time. Let me just go to that one. Here we called it standby. So what happens in standby? So if this condition is met, then it will, you can see the first step is disable everything in flight software. So by default, I want a clean slate. Then I'm going to zero all my gateway messages. So that was that method we saw earlier. So as I'm transitioning between different flight modes, I want all my gateway messages to be clean and zero. So I'm not starting out with some legacy information. Then there's this method that says set all but current event activity to true. We want to avoid, because if mode request is standby and we're running our simulation, mode request is standby every single time step. And we don't want to run all these commands every single time step. We only want to do it once. So when an event gets triggered, this event, for example, standby, initiate standby, will no longer be available. So this command, so I can, let me finish that thought. So if this is standby is no longer available, I can still switch to, let's say, inertial 3D. That's this event called initiate attitude guidance. That's cool. But if I want to switch back to standby, it would no longer be checked because this event is no longer active. So this method, when you're switching these flight modes, it sets all the events across the entire simulation to being available, to be true, except for this one, and that's our own. So that means if I was in inertial 3D and I switched to standby, the inertial 3D event becomes available again, and I can switch back and forth all day long. So that's what this final line does. And instead of, you could have just set events individually on or off. You can do that too, but that's tedious because as I add an event, I have to remember to go turn it on and off in all the other switching codes, and that's kind of tedious. So that's why I made this one method here, where basically it loops through all the events in the system, and unless it is this one, it'll turn it on and make it available. So standby, what does it do? It disables, it zeros, and makes everything but standby available. So you can see nothing is going to run in flight software. That's why the standby mode just turns everything off, and you just have an inert spacecraft tumbling, orbiting, doing what it does, but no flight software is running. Now here in the first sim, we had inertial 3D. right? If we looked at our actual code, inertial 3D, then we're going to switch to direct inertial 3D. So inertial 3D, we've given it a unique name, same process, time step. We're turning it on. There is mode created and available. The condition will be, is mode request equal to inertial 3D? And if yes, we're going to assume we're switching to this. So therefore, we're going to disable the task 0 again. That's always the standard stuff. But now we're also going to call enable task. So on self, we can create enable task and give it this task name. And this inertial 3D, if I search here, this is the task where we added inertial 3D pointing and the attitude tracking error module. So that mimics these two modules happening in that inertial 3D task. So we've turned that one on. And the next module we want to turn on is the MRP feedback with the reaction wheel motor torques, because that'll connect this. And this one should have been configured to connect to the wheels and get wheels, and I'll show that in a moment. But these are the two tasks I need to run in the inertial 3D mode. And so that one is there, and I have MRP feedback reaction wheels task. That's also gonna be activated. And then that's it. And then I want to make sure that all the other flight modes are available so I can switch back and forth, except for the current one. I don't want to keep reinitializing and running attitude guidance. That's a lot of wasted cycles. So you're starting to see the pattern. Direct inertial 3D, which is the second one we had here, we just wanted to run a different task that had MRP feedback configured, a separate copy of MRP feedback configured to directly connect to the external force torque module. So in this case, we disable all tasks, we zero the gateway messages. We're now running the same inertial 3D pointing tasks as we did in the others. So that task we keep on or turn on again. But then I have a different task, which is MRP feedback task. That's the one that doesn't use reaction wheels. And it was configured to talk to that external force torque. And then again, the last step is I'm making all the other events available, setting that to true, except for the current one. So I don't re-trigger the current one over and over again. Those are the two that we need for the current scenario. Hill pointing, it's the same thing. You can see all of a sudden there's a hill pointing task, but we're still doing it with the reaction wheels. Initiate sun safe pointing, that has a sun safe pointing task, and then I'm using MRP steering. Velocity point, that one uses the velocity pointing tasks, but MRP feedback with reaction wheels. So you start to see you can mix and match different flight modes to use different stuff. And the steering reaction wheel one just uses hill point tasking with MRP steering. So now we have a whole slew of different flight modes. And if you wanted to change them, really all you do is change one name here, or you can make 6 different scripts, change different combinations of flight modes, and just run the same flight software, same dynamics. It makes it much easier to reuse all that code, you know, across several different analysis and simulation scripts. So cool. Now that we're there, the last thing we should talk about a little bit is setting up these different modules here and connecting them. So, for example, MRP feedback control and set MRP feedback reaction wheels. So this is the one that sets the MRP feedback module up where it will be connected to the reaction wheel motor torque module. No, I'm sorry. This is the one where it's connected to the external force torque module. So the guidance in message actually comes from a standalone message. This is how we get all these connections across tasks. So we're going to subscribe to that. The vehicle config is just a standalone message. We subscribe to that. Now we have to add ourselves the MRP feedback control data. So that's the MRP feedback one. The commanded out torque is going to be written to a standalone direct commanded torque message. And I set up the gains that we want to use and integral limits of that MRP feedback. In contrast, I'm using the same gains and everything for the one with reaction wheels. But here, let's see what's different. I'm subscribing to that. I'm subscribing to the reaction wheel message. So from SimBase, which we provided as an input argument, dynamics model, that was the instance of the class for all the dynamics. Within it, there's this variable called reaction wheel state effector. That's the Basilisk module and its output message. So I'm subscribing flight software to read the reaction wheel speed message. I need to read the reaction wheel configuration parameters. So you can see this module has to configure and read in optional stuff. That's why I ended up creating 2 different MRP feedback modules, because they really have to be set up and configured differently. And then the guidance in message is still from the standalone. That's the same like what we had here. So that was the similar. But now the output message of this one needs to write to a commanded torque message. And here it wrote to a different one again that was connected to the wheels afterwards. Sorry, this was connected to the external force torque. This one now gets connected to the wheels. So I'm redirecting and I'm adding this output message as an author to this other message. So when this module wants to write to this message, it will write to this message instead. So it's a redirection or adding it as an author. But you can see the patterns now, how this all goes together. MRP steering, similarly, we get connected, rate set, rate servo, vehicle config, we looked at, reaction wheels, that was pretty straightforward. The reaction wheel motor torque now, it subscribes to this commanded torque message, right? That was the one that came out of the MRP feedback here. That was a standalone message that connected those two. And yeah, that was it. Where's the attitude tracking error? I would like to see that one quickly. Where do we set that one up? And gateway. Okay, let me just search from above. This is good live testing. So I'm creating all these modules, tracking error data. Let's close this module, set attitude tracking error. Okay, I was just blind, I didn't see it. Okay, so here, for example, the input, simple nav, right? We always use the simple nav sensor signal. So its attitude out becomes the input to the tracking error module, always. But this was a module that was repeated across tasks. So to make sure it always reads in the proper attitude reference message, the attitude reference message is not connected to a particular hill pointing, inertial 3D velocity pointing output message, but rather it's connected to the standalone message. And as we illustrated before, the inertial 3D mode, the hill pointing tasks, or the velocity pointing tasks, all at the end write to this standalone message. And only one of them is going to be executed at a time. And that's how that magic works. And then the attitude tracking error also writes to a general external attitude guidance output message. So this all gets configured in this way. Now, if we run this script for 10 minutes, it'll be one type of pointing with wheels, and another 20 minutes, it'll run there. So I'm inside examples, bskSim scenarios, and I'm going to run this at scenario attitude feedback. Just takes a moment, and you could see the guidance, and it was running. So this is up to 10 minutes right now. And I pulled all that data and logged it, and you can see how all of the stuff was converging at that point. And how we did all that. Okay, so hopefully something useful. There's a lot of ways you can configure this, but this gives you an idea now. The big takeaways are with events. Let me go to flight software again. Sometimes chunking up all the modules into tasks, that in events we can disable tasks, enable tasks, but the way you connect these chunks of code sometimes requires external messages that everything writes to. That becomes the conduit, the gateway from which all the data should flow through. So subsequent modules only have to subscribe to one message, and you don't have to resubscribe and reconnect your networking topology. So that's the big benefit of how we're doing this. Hope you enjoyed and have fun coding with this.